Hello everyone. So we have done with the conjugate beam problems on simply support beams. The next type of problems are cantilever beams. Okay, so in this cantilever beam, they've asked you to find determine slope and deflection. It's a cantilever beam fixed at A, free at B, and there is a load W acting at B and spaced at a distance L. So first, as it is, you have to draw the deflected shape of the beam. End A is fixed and end B is free. So end B gets deflected more because the load is also acting at B and it's a free end. And once you draw the deflected shape of the wave, apply the boundary conditions. That is, there's absolutely no rotation and deflection happening at A. So theta A and delta A is 0. There's maximum deflection and rotation at B. So this is delta B and theta B. So you have to find slope and deflection at the free end. That is at B. So as usual, draw the deflected shape of the beam. The next step is you have to draw the M over EI diagram. So B is free end. So at free end, you draw the bending moment diagram, that is 0, and end A, at end A it is maximum. That is W into L. So it is WL over EI because it is M over EI diagram. So this is WL over EI. After this, you have to make this M over EI diagram a conjugate beam. Now to convert this into a conjugate beam, so end B. Now end B is free end. Free becomes fixed, fixed becomes free. Okay, so now end A is fixed. Because end A is fixed, it becomes free. So don't draw any support here. Whereas end B is free end. Free end should become a fixed end. So fixed end, just draw the support here. So once you draw this M over EI diagram with respect to this first diagram, then just show end B as fixed support, and we are more interested in shear force, so that's why just show only the vertical force. Actually a fixed support will have horizontal movement, vertical movement, and a third one is rotation, but a matter of interest is only the shear force. The shear force is only acts vertical, so we'll show this fixed end, fixed support, and then only show the vertical force, that is VB. So VB is nothing but the shear force. Okay, so once you show this, next is as usual, calculate the maximum slope and deflection. Now theta B in real beam. So first we'll find theta B and delta B. So theta B in real beam is equal to shear force at B in conjugate beam. Now if you want to find the shear force VB, it is nothing but this is VB is acting upward. Then check out how much total load is acting downward. Now this is a linear triangle. Okay, this is a linear line and this is a triangle. So area of a triangle is half into base L, height WL over EI. Now always here, because it's a cantilever, it is, you have to show it in the negative side, but you should not use this negative sign here because area can never be negative. Only the M over EI diagram, you have to show it like this on the negative side. Okay, then half into base L into height WL by EI. This is the area. So area is nothing but theta B is equal to WL square over 2EI. So here the simple logic is total load acting downward should be counteracted with the total shear force acting upward. So this load should be stopped by this force which is acting upward. So this is theta B. Similarly, calculate delta B. So delta B is nothing but the same thing. Delta B in real beam should be, so because you're finding it B, so that would be bending moment at B in conjugate beam. So delta B is equal to, again, area of this triangle into its CG distance with respect to B. So area of a triangle is half into base into height, then CG with respect to B. So CG with respect to B is, again, you're measuring centroid of the triangle measured from the apex of the triangle is 2/3. So it is 2/3 of L. So 2/3 of L, it is delta B, WLQ by 3EI. This is how you calculate theta B and delta B. So the steps are simple. Only thing you have to draw, first thing is this is the given problem. Then draw the deflected shape of the beam. Once you draw the deflected shape of the beam, you'll know what you're supposed to find out. So you have to find out here theta b and delta b. Next, as usual, just draw the M over EI diagram. With respect to this first diagram, draw M over EI diagram. That is bending moment over EI diagram. After that, just check fixed becomes free. Again, you don't have to show anything free because this is a free support. Fixed becomes free, free becomes fixed. So for this, with the red mark, I've just marked here the supports. You can see here, only the at B, the free end should be made fixed, and because it is fixed support, only show the vertical force. Okay, main matter of interest is vertical forces only. So we're ignoring horizontal and horizontal force and moment. So only show vertical forces. So we have to find out this vertical. To find out this vertical is the area of this diagram. Okay, M over EI diagram. Okay. So similarly, the next type of problem is, okay, find maximum slope and deflection. Also calculate deflection at the load point. Now the deflectant, the load P is acting at C, which is away from B. So end A is fixed, end B is free, and at end C there is a load P acting, and now it is placed at a distance L by 4. It means 1/4 the distance, and 3/4 is there is no load. Okay. After this, draw the deflected shape of the beam. So end A is fixed. So up to certain length, it will not deflect, and this is the deflected shape of the beam. Now you have to find the two things. You have to find maximum slope and deflection. In addition to this, you have to find deflection at the load point. Now you can see here, because it is getting deflected, obviously the deflection is maximum at the free end, and the load point, at the load point it is delta C, and at B it is delta B. Then just draw a tangent. That means just draw a line like this, and this would be theta C. If you draw a tangent here, this would be theta B. You have to find out all these. Okay, so first thing is calculate maximum slope and maximum deflection. Okay, once you draw this, next is M over EI diagram. To draw this M over EI diagram, you have to draw always M over EI diagram with respect to the main diagram only. Only we are going to make some changes in the end here. That is add conjugate support. So check this out at B. Okay, B is a free end. So there is no load, and that's why bending moment is 0. Next, there is no load between B and C as well. So of course the bending moment would be 0, so draw it as a straight line. Next, at P, there is a load acting now. So P into L by 4, force into its perpendicular distance. So the maximum deflection or the maximum bending moment would be at A. So it is PL by 4. So PL by 4. So P into L divided by 4. Because it is M over EI diagram, again divide the ordinate by EI. So again, this is a point load, so linear bending moment. Then join this. So the bending moment looks like this. After this, you have to show the conjugate supports. So conjugate supports is nothing but, now see here, again, free fixed end becomes free. Don't show anything here. Free becomes fixed. So at B, just show a fixed support. Once you show the fixed support, then we'll show the vertical force here. Again, why vertical? Because we are interested only in shear force, vertically acting upward. So this triangular load is acting downward, and this, to stop this triangular load, the shear force is acting upward. So that is VB. Okay. So now let's calculate theta B and delta B. So theta B formula is theta B in real beam is equal to shear force at B in conjugate beam. So shear force at B, that is shear force means only this triangular load. It is half into base L by 4, height PL by 4 EI. So this is the theta B, and that would be maximum load. Okay. Next, similarly, calculate delta B. So delta B is nothing but delta B in real beam is equal to bending moment at B in conjugate beam. Bending moment at B in conjugate beam. Okay. So now bending moment at B in conjugate beam at this point B is nothing but half into base into height is the area of the load. Now CG of this area from point B. The CG of the area from point B is 3L by 4 plus centroid of a triangle measured from the apex is 2/3 of L by 4. So we're going to add this. So this complete distance would be delta B. When you solve this, you'll get 11 PLQ by 384 EI. Now they have also asked you to calculate deflection at the load point. So maximum slope and maximum deflection would be at B. So we have calculated theta B and delta B. In addition to this, you have to also calculate deflection at the load point. So that is theta C and delta C. So theta B is equal to theta C because there is only one triangular load here which is acting down. Again, to stop this, if VC is acting upward like this, so it would be again half into base into height. That would be same. It is PL square by 32 EI, same like theta B. So even theta C would be same. Next, delta C. Delta C is nothing but same thing again. Delta C in real beam is equal to bending moment at C in conjugate beam. So bending moment at C in conjugate beam. Okay, so again same thing here. Area of this triangle load into its CG distance. So area of the triangle load is half into base into height is the area into its CG. Now CG is, because you're measuring delta C, you have to measure with bending moment with respect to C only. So with respect to C, only this distance. So centroid measured, centroid of a triangle measured from the apex is just 2/3. So it is 2/3 of L by 4. It is only 2/3 of L by 4. So delta C is PLQ by 192 or EL. Okay, again it's same thing. First diagram, deflected shape of the diagram, then M over EI diagram, followed by the conjugate supports. So only the free end becomes fixed with the vertical force. That's it. Everything remains same. Okay. Next type is determine slope and deflection at the free end A. Okay. Now this time end A is free, end C is fixed. It's just the opposite of the previous problem. End A was fixed, B was free. This time end A is free, C is fixed. So accordingly, draw the bending moment diagram first thing. Because it's a free end, bending moment of free end is 0. Then there is no load between A to B. So this bending moment runs straight. Then at B, there is a UDL. So because it's a UDL, from B it goes on deflecting. Now check this out. So bending moment at C would be W, that is 30 into 3 into 3 by 2. So it is WL square by 2. That is 30 into 3 into 3 by 2. Okay. So 30 into 3 into 3 by 2 is 135. So this is 135 kilometers. Now between B and C there is a UDL. Now because it's a UDL, you have to show this as a parabolic curve. So parabolic curve and negative side, because cantilever, the forces will be acting downward like this. So bending moment will be negative. So this is a M over EI diagram. But matter of interest is M over EI diagram, because you have to divide the ordinate with respect to EI value. So same thing again. Here, draw the diagram as usual. Then show the ordinate 135 over EI. Next thing is, this is end A is free end. Free end becomes fixed. Just show the support here. Free end becomes fixed and fixed becomes free. So end A becomes fixed, which will have a vertical force like this upward. So this becomes VA. Okay. So now once you draw this, the next thing is calculate the slope and deflection at the free end A. Okay, slope and deflection at the free end, this portion A. So first we'll calculate theta A and theta B. Okay, first we'll calculate this, then whatever is this, the same thing will be followed here. So theta B, we'll calculate theta B and delta B. because there is a load which starts at B. So theta B in real beam is equal to shear force at B in conjugate beam. So shear force at B means it is at this point vertically upward. So area of this triangle, again it is a parabolic curve. So theta B in real beam is equal to shear force at B in conjugate beam. So theta B is equal to 1/3 of base into height. So 1/3 of 3 into 135. So theta B is 135 over here. Similarly, delta B. So delta B in real beam is equal to bending moment at B in conjugate beam. So bending moment at B in conjugate beam is nothing but same thing again. Half into base into 1/3 of base into height, plus you have to measure the CG. So CG measured from B means you're measuring from the apex. It is 3/4 of 3 because it's a parabolic curve. So area is 1/3 and centroid is 3/4 of 3. So delta B is 303.75. Similarly, if you want to calculate theta A, so theta A in real beam, same thing because we have to calculate at the free end A. So theta A in real beam is equal to shear force at A in conjugate beam. That means here at this point. So it is VA. So VA is equal to, again same thing. This is the area which is acting downward. So 1/3 of base into height. So it is same thing, 1/3 of base into height, 135 over EI. Next, VA we have calculated. Next is delta A. Delta A in real beam is equal to bending moment at A in conjugate beam. So again same thing, 1/3 of base into height. Then CG of this 3/4 of 3. Now you're finding the bending moment with respect to A, so you have to add this plus 2 distance. So 1/3 of base into height, then 3/4 of 3 plus 2 because you're measuring with respect to A. So it is plus 2. So theta A would be maximum. That's how you solve this. So the only important thing here is draw the bending moment diagram, M over EI diagram, followed by the supports. So in the M over EI diagram, we convert the supports. Free becomes fixed, fixed becomes free, and the fixed support which you have modified will just have a one single upward forces in it, vertical forces in it, and that those are nothing but the shear force. So if this is vertical force acting upward, so this area will be acting downward. So you have to compensate both the forces and solve. Thank you.